I think after this presentation, we will actually move to directly to applications. And applications, by the way, it doesn't mean that it would be just click here, a nice example with data. There will be lots of theory as well. So we need to discuss a little bit about priors. And I think I will most probably do this tomorrow, since we discuss about this hierarchy of priors, formally see a little bit more about this hierarchical Bayesian modeling, okay? This empirical Bayes. All right. So I don't have time to sort of philosophize, right? But the question is, if you're going to use a prior on your parameters, what prior do you use? And that's a philosophical subject because it's very subjective, okay? The statisticians will tell you, if you have any knowledge about your problem, use it. If you don't use it, and you try sort of to put the most generic thing because it looks mathematically nice, then you really have no idea what you're doing. So if there is knowledge you have, all right, use it. And I know one of my colleagues from the UK, he wrote a whole book actually, and he makes lots of money consulting on the topic, trying to sort of mathematically summarize the knowledge of experts to come up with prior models that make sense. So that's a huge area on its own. I mean, you can imagine, right? If you go on a table around and you ask people about their prior knowledge, people will tell you different things based on their experience. So how do you write this mathematically down? So there is a way to do that, okay? But the point is, try to use whatever information you have. So if you have some information in a physical context, and we will see this later on applications, if you compute parameters that they are correlated, and you know from physics how they are correlated, use that information. So certainly there is subjectivity in this in the selection of the priors, but still, you know, we are teaching a course on machine learning, all right? So we're going to try to cover the most common forms of priors that people are using in machine learning, and in the context of informative priors, right? Because we will also discuss uninformative priors. I want to give you a flavor today of what we call conjugate priors. We already have seen it, so nothing new. I'm going to tell you that the most common conjugate priors are the priors that are coming from what's called the exponential family, and I deleted the slides because there is too much information there. As part of this exponential family, a very big area involves what's called the maximum entropy priors. Okay? There's actually a very nice book on probability just about that subject alone. Okay? So we already have seen these informative priors, these conjugate priors, but I want to introduce this exponential family because we're going to be using it all over our lectures. And then I'm going to give you some ideas on how to compute uninformative priors. Basically priors that do as little damage as possible if literally you know nothing, okay? But you remember when, I think in one of the lectures on discrete calculations, I show you that even if the prior is uninformative, all right, and you use point estimates and you calculate the posterior mean, the effect of the prior still does smoothing to the posterior mean distribution. You remember how we call that? We did this for the coin problem. So even if the prior is flat, you know, add one smoothing. Okay, that's very fundamental to machine learning. Add one smoothing. So you may want to go back and look again at that after the lecture today. All right, so let me, I'm going to give you a formal definition of the conjugate priors, right? So already we have seen it. So let's assume that we have a likelihood, right, with some parameters theta, and I denote the likelihood here with f. And let's say the likelihood comes from some family of distributions that I call F. Okay? Some family of distributions that have these parameters theta, and so that's where my likelihood comes. And now I'm going to take priors for the parameters theta coming from another family of distributions P, and I'm interested on priors that are conjugate to the family F, in the sense that the posterior also belongs to the same family as the prior. Makes sense? So I have a likelihood from some family, I multiply with priors from another family. If the posteriors are from the same family as the prior, then this family of the priors is conjugate to the family of the likelihoods. And I call this conjugate. So in essence, it makes the algebra simple, right? Because if you have a prior with some parameters, you multiply with the likelihood, you only have to update those parameters in the prior. And as a matter of fact, if you go to Wikipedia, there is a huge, beautiful table that gives you all the conjugate distributions. You can literally go cut and paste for anything you need. You don't have to prove anything, right? So these days, with information being free, especially in mathematics, there is no justification for not knowing. Any question you have, there is an answer. Literally, somebody has answered. Okay? Of course, that also means for every question and every answer, there are thousands of more questions coming every day to advance the field. So there is a loss. The learning curve of new things is as important as learning for you all things. All right. So let me just remind you the example that we have done with these conjugate priors. You remember we did the coin flipping case. So theta being the probability of drawing heads. We took a prior that was a beta distribution. The likelihood can be a binomial or a Bernoulli distribution. So NH is the number of heads, n minus NH the number of tails. So when you multiply the likelihood, theta to NH and 1 minus theta to n minus NH with a prior, which is theta to a minus 1, theta to d minus 1, you realize that the posterior, it's also a beta distribution where effectively you have added to the number of heads a pseudo count of heads coming from the prior to the number of the tails, a pseudo number coming from the prior that is b. So in this case, let's say the binomial distribution is conjugate to the beta distribution. Now, so what you will see now, we have not discussed it before, all right? So these conjugate prior distributions are often associated with what is called the exponential family of distributions, okay? Let me just say that most applications in machine learning, in probabilistic graphical models, etc., they use exponential family distributions because the algebra is manageable. Okay? So what's an exponential family distribution? So a distribution, look, if you look at the likelihood, all right, because we're looking for priors that they are conjugate to this likelihood, the likelihood looks like this nice formula. So X is my data set. I have parameters theta, and the form of the likelihood is some function of theta, some function of X, and then the exponential of r theta dot with Tx. Okay? Now Tx is called the sufficient statistics. Can somebody guess why we call T of X the sufficient statistics? What's the word may imply? So in solving for the parameter theta, right? All right, you can notice r of theta is coupled with Tx only through this term. So you don't really need to know all the data x as they come. You need to know this function of the data x. So for example, let's say if you were calculating the mean through a Gaussian distribution, you don't need to know x1 and x2 and x3, etc. You only need to know x1 plus x2 plus xn. Okay?
You don't need to know h of x.
Well, but you see, the parameter theta is not coming there, so that will disappear from the picture. Okay? So we're only looking, the likelihood, I would like to look at it as a function of theta. Okay? As a function of theta. So this family is called, this is the general equation for the exponential family. If you can simplify the way that you look on the bottom, so if the parameter comes from some k-dimensional space, Rk, and x is also k-dimensional, and if I take this c of theta and with a log I put it inside the exponential, you can get an exponential family of distributions that looks like this, and this is called the natural family of distributions. So rather than having r of theta dot with t of x, you have theta dot with x. Okay? So this is a specialized form, if you like, of the general exponential family. So let me, I don't know if we're going to do this in this course, right? But so let me actually not say anything yet, right? But if we have time in a future lecture, I am going to show you that the representation of distributions, when you look at them in terms of the moments, may not be the most natural and the most convenient to actually do calculations. So when you write the Gaussian in terms of the mean and the variance, that's one way of doing it, but this formalism using this exponential family of distributions may have another representation that's actually computationally more useful, but you don't know about it yet. Okay? So let's leave it there for now. One example of exponential family of distributions. So if I look at the Gaussian, I am taking here the variance to be equal to 1, and my only parameter is the mean that I denote as theta, right? So this is my likelihood function, and I take just one data point x. So you can actually immediately write this in this natural family of distributions. You can see if you expand the exponential, you're going to get e to the minus x squared over 2 divided by 1 over square root of 2 pi will give you h of x. All right? Then you're going to get a function of theta. You're going to have e to the minus theta squared over 2. So psi of theta is going to be theta squared over 2. And then when you take 2 times x times theta, all right, 2 and 2 will cancel. So t of x is x. And so you have theta dot x, basically, if I want to write this in a most generalized way. If you try to expand this, and you want to make the parameters involve both the mean and the variance, so if the mean and sigma squared, the vector, or here I don't know, I take the mean and the standard deviation to be my parameter theta, you can actually write this in the exponential family, and I want you to go and test it when you go home, okay, that my algebra is correct, and you can see that t of x consists of the vector x and x squared over 2, or minus x squared over 2. R of theta consists of these parameters, and the rest are what is given there. Okay? So actually, you know what that tells you? That the sufficient statistics is not just x, all right? It's x and x squared. Okay? So x and x squared, because my parameters here are both the mean and the variance. Okay, now, no more little trivial examples that give noise. If the likelihood comes from the exponential family, the question is, how does the prior, then the conjugate prior looks? The conjugate prior will also be from the exponential family. We have exactly the same identical form. I don't put this h of x, there's no x here. It's a prior. So I'm going to have, look at this. My prior is going to be r theta dotted with mu, where mu is a hyperparameter on the prior, and psi of theta is going to be there, but times lambda. So when I multiply the two things together, you notice that t of x is added to m, and you notice the 1 from there is added to lambda. So the posterior immediately, if your likelihood is from the exponential family,
You know the prior is going to be from the exponential family as well, right? That's what we work with conjugate priors. And the posterior immediately has a very nice formula where you went and added to the sufficient statistics T of x mu, and you added to that coefficient 1, you added lambda. So that's the algebra looks very simple, so that's what is useful about this type of distributions. So let me, I have to admit, I don't know how much algebra you did in your previous course. If you only look at the formulas that I'm going to be giving you with these examples, maybe you're not going to learn much about from where they come, okay? So you have once in your life, maybe you need not to trust the formulas I give you, and do them. And the way to actually learn how to do them is to have in front of you a book, a chapter that has everything about, you need to know about the Gaussians, how you marginalize, you multiply, disclosing the square procedure, etc. But let's look at a trivial example. I'm going to take a likelihood that comes from a Gaussian, where the only parameter is the mean, theta. Okay, so sigma squared is no. So that's my likelihood. And I take one measurement, right? So that's my likelihood for that measurement. Now, you have to believe it, right? And there's a table, as I mentioned in Wikipedia. If your likelihood is a Gaussian, the conjugate prior for the mean is a Gaussian, right? So the conjugate prior will be from the exponential family that is where the Gaussian is part of. So it will be a Gaussian with mean mu 0 and variance sigma 0 squared. Now, if you multiply the likelihood with a prior and you normalize, the result, obviously, since they are conjugate, it will come to be a Gaussian. And here is the inverse square, or the inverse of the variance of this posterior. How do we call 1 over sigma squared? You remember the language?
Precision?
No, if you have the variance, 1 over the variance, how do we call it? And books like Bishop like to use that a lot because it makes the algebra simple. So 1 over the variance is what? Somebody said it, actually, I didn't. What did somebody say? 1 over the variance. What's the name of that? Say it louder. It's the precision. All right? So the precision of the posterior is the precision of the prior plus the precision of the likelihood. And the mean for the posterior comes to be a weighted mean of this prior mean and your measurement x1. And the weights basically are proportional to the precisions. Okay? Now, you may say to me, what do I need to do if I go home to actually do this calculation? Well, what you need to do is take this, multiply with a Gaussian, and then you have to expand this and expand that, and you need to get a new Gaussian in theta, and you have to do what is called close the square in theta. So what is close the square? You remember a Gaussian, right? Let's say in theta, what will it have in the exponential? E to the minus theta minus something squared divided by 2 something, which is going to be the new variance. So you're going to need to find something to create a square, theta minus something squared. And that something is going to be your new mean, and whatever you get in the denominator is going to be 2 times the new variance. All right, so you collect all the terms and you close the square, and when you close the square, you get this wonderful formula. For this simple problem, when we do regression and we have to close the square, the formulas will be so lengthy, some of them will have to be extended over 2 pages. But you have to do them by hand. No computer program is going to tell you what they are, okay? So, and actually you can do even fancier things. If you know the posterior, which we just computed, all right, and you multiply with the likelihood and you integrate in the parameter space, you will get this wonderful distribution, which is what distribution? How do we call that distribution?
Predictive.
That's the predictive distribution. And somebody will say, okay, the posterior is a Gaussian in theta. The likelihood is a Gaussian, I see it on the top. How do I integrate in theta? Well, it's very simple. You are going to close the square to get something like a Gaussian inside the integral. And when you get an exponential that looks like a Gaussian and you have to integrate it in theta, what you will be left with will be the normalization constant of the Gaussian. Exactly, thank you. All right? So basically, you don't really need to do everything, but you need not to hesitate to bring this together in the form of minus e to the minus theta minus something square over 2 something square, all right? And then, you know, it's a Gaussian, the normalization of that Gaussian, and that's why I don't want to do the algebra, because it's part on the slides of another course. And then eventually, you get a wonderful formula for the predictive distribution that is also a Gaussian. By the way, this is for one data point. You can extend this to multiple data points. All right, so if you have multiple data coming from this Gaussian, okay, you can actually write the likelihood, and I actually give you here in new interesting forms. You can write this, the variance, no, sorry, let me see. So this is the posterior, all right, so if you do the same algebra, the posterior, you can write the variance of the posterior as sigma squared divided by n plus n0. N is the number of data points, and n0 is the pseudo number of data points that come from the prior, and it comes out to be sigma squared over sigma 0 squared. And the mean of the posterior comes to be, usually if you only do like an MLE estimate, the estimate for the mean will be sigma xi over n. Here, because we are doing a Bayesian calculation, so we have sigma xi plus mu 0, so that's the prior mean times the prior counts, like the prior number of experiments, divided by the total number of experiments, n plus n0. Again, the interpretation is not needed, but you get a wonderful formula. So if you, let's say, write a paper and somehow you treat things as integrals and complicated forms, and there is a nice answer that looks like this, we're in trouble, all right? Because something that's analytical has to be used as analytical. So this is a little table that shows you for different types of likelihoods, okay? The conjugate prior, all of this is from the exponential family, okay? So you can see this. And maybe you did this when I was away in another lecture. We have, let's say, multinomial distribution. The conjugate prior is a Dirichlet distribution, and the posterior comes to be a Dirichlet distribution. So again, Wikipedia has a much more detailed table with many, many distributions that fall in the exponential family. But keep in mind, unfortunately, not all distributions are in the exponential family. So there are important distributions that are not as easygoing in doing algebra as you see here. Okay, I want to do one example. We have actually 6 minutes, okay? So people, who use this, conjugate priors, they say, okay, mathematically, they're nice because the posterior is the same form, but really, there is no other reason to use them, right? It's only for mathematical simplicity. So, for example, if you have a coin and you put a prior on theta that says the coin is fair, somebody says, how do you know it's fair? So maybe, a possibility will be, rather than using a beta distribution that says the coin is fair, how about if you use a mixture of 2 beta distributions, one for a fair coin and one for an unfair coin. So let me tell you the result. If you use a mixture of priors that they are conjugate to your likelihood, it comes out that the posterior is a mixture of the same type of distributions. So basically the distribution, the posterior, is going to be some different mixture, not 0.5 and 0.5, some different of some beta distributions. All right, each of them will be the posterior under its prior. And you may say, where is that coming? And everything is on this slide that contains a lot of information. Okay? So, let me, we have 3 minutes, and most probably we will finish this tomorrow. I am going to take a prior that is a mixture of let's say, k priors. So wi pi of theta, where I goes from 1 to k. So I have k priors, and I'm going to take a mixture of these k priors. The sum of the weights have to be equal to 1, all right? W1 plus W2 plus Wk equal to 1. And I'm going to call Wi the prior mixing coefficients. And maybe you can guess why I'm going to call them the prior mixing coefficients. Because when I compute the posterior, some new weights are going to come back, right? The posterior is going to be computed given my data, and those will be the posterior mixing coefficients. Will be the mixing coefficients of the posteriors after I have seen the data. The calculation is actually very simple, okay? So if you want, so this is what I am going to use for my prior, and I'm going to write this using an indicator variable z. Can you understand the notation here, what z is? So for example, p of theta, given that z is equal to 1, is my prior pi 1. So z is what? It's an indicator variable that tells you which prior to use. Okay? And I like to use a z because I will go and compute the posterior of z. Okay? So, if you calculate the posterior, let me go fast, right? We have 2 minutes and I'm going to return tomorrow to it. If you compute the posterior of theta, okay, it comes out, all right, that you get the posterior under its prior, so as if you were using that prior alone. So this is the posterior up under its prior, and you can see that's the prior I times the likelihood divided by the normalization factor, and these are the posterior weights. Okay, these are the probability. These are the posteriors. I put them here with blue. These are the posterior probabilities of the z's given my data. So they are the posterior mixing coefficients. Okay, and the proof is actually on the last line. Okay, so there is nothing fancy about it. And so I'm going to come and do this example tomorrow. We took 2 priors that have parameters A1, B1, A2, B2, beta priors with equal weights. And eventually, when I calculate the posteriors, all right, it comes out that there are mixtures with some weird coefficients that you can compute of 2 new beta priors, 2 beta posteriors, all right, one for each of the priors. And the plot here shows you how the prior looks like, and the blue line is how the overall posterior looks like. Why do we care? And I mentioned so many times about this marginal likelihood, because to be able to calculate these posterior mixing coefficients that you see there, you're going to have to compute for each prior, for each selection of the prior, you're going to have to calculate the marginal likelihood. Okay? And the marginal likelihood, I had done this in a previous lecture. I gave you the formula for this problem, so this calculation has to come in. So this looks trivial, but the calculation is actually very informative. So I want you to look at it, study it, and I noticed the students from last year, no, actually from 2 years ago, they came and they told me what I had wrong on this slide, because I had a piece of, on my notes, a piece of note from students saying, you know what, these coefficients there, you messed them up, and they're like this, and they were right. Okay, so hopefully. All right, the light is on, so we can continue speaking to a vacuum
in a room of 500 people with 3 in the audience, just in case anybody listens to this tape, to know that life can be very miserable. All right, so let's get out of reality and try to talk a little bit about machine learning. So I stopped last time about using a mixture of conjugate priors. I don't know if any of you took the time to actually read the slides. So I'm going to make a 3-minute effort to repeat what it is. So we have a prior that's a mixture of conjugate priors, okay? So Wi are the weights before we see any data, so they are the mixing weights. And I introduced the variable z, which is like a hidden variable, typical of mixed models. If z equal to 1, means I pick up prior 1. If z equal to 2, I pick up prior 2. All right, so this is, so we're obviously going to need a prior on the z variables to do this. So if you try to compute the posterior on the parameters of the model, so what you will need to do is, you're going to need to put the prior, which is the summation, times the likelihood, divided by the normalization factor that I call an A. So I can put this A inside, just for convenience, and I have a summation of the mixture components of Wi over A times the prior times the likelihood. And I'm going to rewrite this equation for reasons you're going to see now. What I'm going to do is, I am going to multiply this equation here inside the argument by the integral that you see on the top. So there's going to be on the numerator Wi times this integral, divided, of course, by A. So Wi times this integral divided by A, that's what I call Wi prime. And you can immediately see that this term here, this is the posterior of my model if I use the prior I. So you anticipate, all right, you anticipate somehow that these coefficients Wi prime are the posterior coefficients of the latent variable z. Right? Once you observe the data, it tells you the probability of using prior 1 or prior 2. Okay, so these are the posterior mixing weights, if you like. And indeed, you can actually, if you use Bayes' rule for the z variables, so given the data d, this posterior of z is the prior times the likelihood divided by the normalization factor. And this is the marginal likelihood if you use the prior I. And you can see the marginal likelihood here, right? That's what you get from Bayes' rule. That's the marginal likelihood if you use prior I. So indeed, these are the posterior mixing coefficients. They sum to 1, and we have a very nice result that says that if you use a mixture of conjugate priors, the posterior comes to be a mixture of the posteriors using each prior separately. That's a nice result. Now, do people use this idea of mixing conjugate priors? Most probably not, because it involves a lot of the calculations here. So you need to calculate these mixing coefficients, and that requires to evaluate the marginal likelihood. And as we said, that's a heavy-duty calculation. So very few people use this mixture of priors. But still, the result is very powerful. And we apply it to an example in the tossing of a coin. So if we have a prior that the coin is fair and a prior that the coin is unfair, we can take prior mixing coefficients 0.5 and 0.5, and we can actually show, we know what the posterior will be for each prior. We have derived this a few times in earlier lectures. There are also the posterior beta distributions. And these are my the posterior mixing coefficients. And we even actually have derived the posterior mixing coefficients, because to derive the posterior mixing coefficients, you need the marginal likelihood for each prior. And the marginal likelihood, for those who read the notes, is written as the ratio of marginalization factors of the likelihood prior and posterior. You remember? So what is BA1, B1 is the normalization factor for the prior one. What is BA1 plus N1 plus B1 and N0 is the normalization factor for the posterior. And what is N over N1 dot factorial is the normalization factor from the likelihood, which is binomial. So everything is very, very easy, but this is a very good example to actually do by hand and then test it in the computer. And you can see here a beautiful prior that is a mixture of two priors, right? You can see it's multimodal, and then you can get a nice posterior that better captures what's going on than simply using one of these priors. So this is a very nice example that you should study. By the way, a lot of the details are hidden inside these little programs from Murphy's MATLAB toolbox. And if you really want to learn the details, you hit that toolbox and you see what is there. Because there are fine details that they are not in the slides, they are not in the book, so there is something to learn there. It's not like that I'm going to advocate that you will use these MATLAB programs, but if you want to understand the theory, you can sort of be impressed that this little example can be simulated in a few lines. Because at the end of the day, if you have all the formulas, you have this ready to go. These are beta distributions. Really, there is this a few lines of a program, assuming you know how to compute all these nice beta functions and the beta distributions. So the posterior comes to be a mixture of two betas, but notice, even though we started with prior coefficients 0.5 and 0.5, the coefficients are not 0.5 and 0.5. These are the posterior mixing coefficients. Okay. All right, so we have to talk a little bit about non-informative priors. So if you don't really know anything and you're not comfortable using any informative prior, non-informative prior is the way to go. But assuming that you have a lot of data, if you don't have any data, this can be a very risky proposition. So I will discuss today, right, when you change parameterization, when you change parameters in your problem, the distributions that you have need to satisfy certain invariance relations, okay? So when you use non-informative prior, so for example, if you take a variable and you say it's uniform, it's, the probability it's equal to 1 or something like that, and then you go and you change variables from theta, you go to theta square, you realize that what you had in mind as a uniform distribution is not anymore a uniform distribution. So we will have to be sure that we satisfy these reparameterization equations and we understand exactly what the implications are. So let me see what is non-informative prior, right? So let's say that you have a likelihood that has some parameter lambda, and lambda, let's say, can take k different states. So one of the typical example of a discrete non-informative prior will be a prior that assigns a probability 1 over k to every state, right? Makes sense. You have k of those. You say, I don't want to select one state versus the other, so you put a probability 1 over k. The question is, what happens if k goes to infinity, and in particular, what happens if lambda is a continuous variable? So if it's a continuous variable, the problem is the distribution cannot be normalized, and that's what we call an improper distribution. Now, in the books and in papers, you will see lots of people using improper, non-normalizable distributions, and you say, how is that possible? Well, you can have a prior distribution that is improper, but somehow the posterior comes to be proper. All right? And at the end of the day, if you care about the posterior, and the posterior is proper, you're all right. So for example, if you put, and let's say a uniform prior on the mean of a Gaussian, so if your likelihood is a Gaussian, and you want to compute the mean, and you say, I'm going to put a uniform distribution on the mean, literally, the posterior is normalizable if you observe one data point only. That's not bad. So if you observe one point, you fix the mean, really, and so the posterior is normalizable. And you can extrapolate, actually, that if your unknown is the variance, you need 2 points to fix the variance. Okay, so if you have 2 points, the posterior is normalizable. All right. Now, I remind you, we discussed this in passing last lecture, that a lot of these non-informative priors, even though we call them non-informative, so for example, if I use for the coin problem a beta distribution with parameters 1, 1, and you compute the posterior mean, you have this Edwan smoothing. So in principle, it is uninformative, but not really uninformative as to doing nothing. So in calculating this posterior mean, literally you add this regularization terms 1 and 1 plus 1 on the denominator that addresses the overfitting that you observe when you operate with the maximum likelihood estimate that you see here. So the question is, does this mean that the distribution beta 1, 1 is not uninformative? What do you think? So I remind you, what's the equation for the beta distribution? It's theta to what? To a minus 1, 1 minus theta to b minus 1. You remember? So obviously, if a and b equal to 1, this becomes a uniform distribution. All right? So, but it seems here that the uniform distribution still does something. So is there any other sort of parameters for the beta distribution that actually make the beta distribution literally uninformative? And I am going to discuss this as we go in the lecture today, and you will see there is another choice that we can use to really make this uninformative. Actually, the best choice of all, okay, that nobody is using, is to take the distribution beta 0, 0, that contains 2 equal masses at 0 and 1. Obviously, this is not normalizable. But again, the posterior can come to be proper and normalizable, especially if you observe one head and one tail. All right, so this is a singular non-normalizable distribution consisting of 2 masses at 0 and 1, okay? Obviously, if your parameters A and B are equal to 0, they are not going to change anything even in the posterior mean, right? So this will be literally uninformative, but again, nobody is using it because of these pathologies that I mentioned here on this slide. Now, it's going to come up to your surprise that actually the best uninformative beta distribution you can use is one with parameters 1/2 and 1/2. Okay? And so it will take us a few slides to arrive on this result to show how this distribution is coming about. Okay. A reminder of this concept of changing the parameterization, changing the variables basically, and how the distributions behave. So if you have a distribution, let's say a prior on lambda, and you define a new variable eta through the formula lambda equal to eta squared, the distribution on eta is given by this wonderful formula. All right? And you can actually, the best way to remember this is that the probability mass is conserved. So the probability of eta times d eta is the probability of lambda times d lambda. Okay? And d lambda over d eta is 2 eta. So you can see, for example, if the distribution in lambda is a uniform distribution, the distribution in eta is not uniform anymore. So when you say you're using uniform distribution, be sure you have the correct parameterization, because if I go and change it, obviously the distribution is not anymore uniform. By the way, this formula that you see here is only for distributions, right? If you have a function and it's constant, and you have a function f of x, and instead of x you use x squared, f of x squared is also constant. All right? But distributions don't behave like that. Distributions have to conserve probability mass. So in some sense, when you operate on the likelihood and you do reparametrization in the likelihood, nothing changes because the likelihood it is treated as a function of the parameters, all right? So that is not an issue, but in the priors, you need to be sure that this equation is embedded in your model. So you know, if you're gonna come up with some new prior, you better be sure that it transforms the way this, the first part of this equation solves. Okay, so I'm going to go very fast through the slides because they're important, but I only can give you the final results. So let's take a density, a likelihood model with some parameter mu that looks like this, okay? And you can actually, so you can think of mu being the mean of this likelihood model, all right? If it is a Gaussian, let's say mu is the mean. So can you agree with me that if you shift x by some distance and you shift mu by the same distance, this model doesn't change? Can you see that? All right? So effectively, if I change x to x plus c for any arbitrary c, and I do the same transformation on mu, then the new distribution has exactly the same form. And this is what we call a translation invariant distribution, okay? So the question is, can we come up actually with prior models that are translation invariant? And the key idea here is, if you're gonna have a prior model and you look at the probability mass between some points A and B, you want to be sure that if you move the whole density by some arbitrary distance c, the probability mass between A minus c and B minus c is the same. Make sense? If you move the whole thing by some distance, right, and you look at the probability on the interval A minus c and B minus c should be the same as the probability mass between A and B. Now, if you do the calculation and you say this probability mass should be equal to that, and you change variables, immediately you can see that P of mu has to be equal to P of mu minus c, and for any arbitrary constant c. And the only way for this to happen is if the distribution is constant. You can try anything you want to. The only way for this to take place is if the distribution is constant. You know, this is the flat prior that we have looked before. And again, if you think of the mu to be the mean, let's say, of your likelihood model, if you observe one data point, you can actually see that the posterior is normalizable. Okay, so you only need one data point. An example of a translation invariant prior would be to actually, that is non-informative, would be to take a Gaussian, all right? So you take a Gaussian for the mean and take the variance to go to infinity. So in some sense it's conjugate because if your likelihood is Gaussian, right, the prior is Gaussian, but to make this an informative, to look like a uniform distribution, you have to take the variance to go to infinity. Okay, so it is not unusual for people to use this type of uninformative priors by using conjugate priors and then taking them to the uninformative view by making the variance to go to infinity. Now, there are many reasons why you should not do this. You should not use this, but you know, but that's for another discussion. All right, so a scale invariant prior. So let's say you have a likelihood that looks like that. You can actually show that if you scale C, I'm sorry, if you scale x, so if you define some new variable x hat that is some constant c times x, and you do the same thing for sigma, you can show that the distribution remains exactly of the same form. And this is what we call a scale invariant distribution. By the way, in showing that this distribution looks like that, obviously I use the change of variables formula that you saw in a previous slide. So there is a half a line calculation to do this. So don't take this for granted, or don't think of this as a change of arguments in a function, because that's not what it is. We're changing probabilities from x to x bar, right? But my conclusion here is this distribution is scale invariant. We change the scale from dollars, we go to Swiss francs, still the equation looks the same. So can we find priors that are actually scale invariant? So what you need to do is, if you take the probability mass from A to B, you want to enforce that that probability mass is the same as the probability mass from A divided by C to B divided by C, okay, for any arbitrary constant C. And if you change the variables in this integral, you can make the domain of integration again A to B, so P of C has to be equal to that, all right? So a scale invariant prior has to satisfy this equation. And again, you can play around, you can do anything you want to. The only distribution that can satisfy this is the distribution 1 over sigma. Okay, and I want you to remember, because sigma is going to be our standard deviation, and we have similar formula for the variance or the precision. I want you to remember that if you want an improper prior on sigma, it's 1 over sigma. Okay, this is going to come up intensively even in our regression models. And an equivalent way to write this distribution is to say that the distribution on log of sigma is uniform. All right, and you can, again, why P of log of sigma is uniform? Because the derivative of log of sigma is 1 over sigma, all right? And so combined with that and the change of formula for distributions, you will see that P of log of sigma is constant. It's 1, basically. Okay, you can actually use a conjugate, you can use a gamma distribution basically to approximate this improper prior, and this gamma distribution is, you take parameters 0 and 0, okay? And because sigma plays the role of the variance or the standard deviation, you will need, as I mentioned before, 2 data points to actually make the posterior to be normalizable. All right, and again, you can think of this scale invariant distribution by looking at the Gaussian likelihood. All right, so if I take the mean to be fixed, and I want to compute, let's say, sigma, and I want to put a prior on sigma, the right prior would be, if it's an uniform prior, would be P of sigma equal to 1 over sigma. You can show, all right, I am not going to do the calculation here. I strongly advise you to do it. If you take the precision, remind me, what's the precision? Lambda? What's the definition of the precision? Lambda equal to what? 1 over sigma squared. So you can show actually that P of lambda, it's actually, from this change of formulas, you get it's 1 over lambda. All right, so, in a lot of problems, and we will actually, when we do the regression model, we will calculate, we will operate on the precision rather than the variance because it makes the algebra easier. And so the uniformity prior for the precision is 1 over lambda, and it's derived basically from this scale invariant prior. And basically, I give you the general formula for the gamma distribution, and you can see if you want to put a conjugate prior on lambda, right, and your likelihood is a likelihood, you're going to use a gamma distribution. And I saw you here the gamma distribution, lambda to A0 minus 1, exponential to minus B0 lambda. So if you take A0 and B0 to be 0, then the only contribution from the prior that you get is 1 over lambda, right? So when you suddenly actually see calculations and you are off by a factor of 1 in your lambda, means somebody has gone and plugged in an uniformity prior on lambda without even telling you, all right? So it's not a mistake, means there is an uniformity prior on lambda. Okay, so talking about uniformity priors, we have to talk about Jeffreys non-informative priors. There is much here to learn, and we can only do this in 5 minutes. So the nice thing with this uniformity prior introduced by Jeffreys is this reparametrization that I discussed before, that the prior, when you change parameters, needs to obey this conservation of probability mass. This prior of Jeffreys satisfies that automatically. So you don't really have to worry about it. You don't have to do anything. It satisfies that automatically. So what is this uniformity prior? You have to define what is called a Fisher information. Some of you will have to learn more about it because it relates to many different topics in information sciences. So you have to define the Fisher information as the expectation on the data distribution, so that's the distribution from where your data come, of the second derivative of the log likelihood. Don't ask me from where it comes, et cetera, et cetera. It's actually, if you go on Wikipedia, after a few pages of reading, or actually not even 2 pages, in half a page you will see how naturally this Fisher information is coming. But what I want you to concentrate is minus the expectation with respect to the data distribution of the second derivative with respect to the parameters of the log likelihood. And what is the Fisher prior then? The Fisher prior is the square root of the Fisher information. And if the parameters you have more than 1, and this is actually a matrix, you are going to have to take the determinant of the Fisher information and then square root of the determinant. All right, so if you have 2 parameters, the Fisher information will be a matrix 2 by 2. So you have to take the determinant and then the square root. Now, the first question is, I mentioned the reparametrization is taken care automatically. So you may say, can you at least highlight why is that the case? And the proof is actually on the equation that you see on the bottom. All right, so if you look at the Fisher information and you change variables by going from theta to phi, you can see that this equation is automatically satisfied. All right, so I am not going to do all the algebra, but when you take derivatives here with a second derivative with respect to phi, this is the second derivative with respect to theta times the Jacobian square, all right? And so when you take the prior will be the square root of that, so you're going to have this is the prior on theta times the determinant of d theta d phi, and automatically this reparametrization equation is taken care of. And actually, that's the only type of priors that everything is guaranteed for you when it comes to this reparametrization, so you don't have to worry about it. Okay, a few examples of the Jeffreys uniformity prior so you can figure out how to do the algebra. If, let's say, your data come from a Gaussian likelihood and your unknown is the mean that I indicate here is theta, so sigma squared is known. So my only parameter is theta. If I collect 10 points, will you agree with me that the likelihood will be proportional to this? I only keep the terms that involve theta. You see that, right? Nothing fancy. So if you take second derivatives with respect to theta, this comes to be minus n over sigma squared, which is a constant, all right? So what is the Jeffreys prior for the mean? It's the uniform prior. The same answer as before, right? So before we introduced this from a different context and common sense, but now you can see Jeffreys prior being the uniform distribution, all right? It comes naturally from his formulation. If you take the variance to be the unknown and the mean to be known, all right, so if the only unknown is theta, you start again with your likelihood and take derivatives with respect to theta. And again, theta is the variance here. So you just take derivatives with respect to theta. And then you remember to compute the, how do we call it, the information? What was the buzzword? Remind me. The Fisher information, okay? I was looking if there was another name for it. So if you try to take the Fisher information, you have to take, for the second derivative, you're going to have to take expectations with respect to the underlying distribution of x. All right, so we're going to have to take expectations with respect to this distribution. And the only x's we have is on this term. And when you take expectation of this, I'm not going to do the algebra, all right? But if you expand it, okay, the expectation of this, and maybe you already remember this from your earlier class, would be, can you tell me what is the expectation of that? Of xi minus mu squared? And a good place to remember actually this is if you remember the MLE estimates and the biased and unbiased concepts of these estimates, that's where you need to take expectation. The expectation of this comes to be what? N times. The expectation of this summation is n times. N times the variance. And that's where n times the variance will give you n times theta divided by theta cubed. You get n over theta squared. So basically, this Fisher information is 1 over theta squared. So if we take the square roots of that, we get the wonderful result that the prior on the variance is 1 over the variance, which is similar to what we had before for the scale invariant priors. So we basically get the same result. So the prior on sigma squared is 1 over theta, 1 over sigma squared. And lots of times you can simplify this and you say the prior on the log of the variance is the uniform distribution. Okay, here is another example. All right, if your likelihood is a binomial distribution, so in n trials you get x heads. Theta is the probability of heads. The mean of the binomial is n times theta. So if you compute the second derivative of the log likelihood and you take expectations with respect to the distribution of x and you use this result, the answer comes to be 1 over theta times 1 minus theta. You only care about the theta factors, right? So it comes that for the binomial distribution, the Fisher information is 1 over theta times 1 minus theta in the denominator. And so the Jeffreys prior is the square root of that. And the square root of that actually gives you a beta distribution with parameters 1/2 and 1/2. So you can see now, we started with uninformative priors of beta with parameters 1 and 1. Then we said maybe we'll use this beta with parameters 0 and 0. But Fisher's methodology says no, the uninformative prior is a beta with parameters 1/2 and 1/2. Okay? So if you use that, people at least will know that you have some idea about the Fisher information and the Fisher prior. Okay? You can actually extend this beyond 2 states. So here we have heads and tails. So you can extend this to a Dirichlet distribution. So can you, I don't know if you took the time to read about the Dirichlet distribution, but did you do that in your previous class? Did you do anything about the Dirichlet distribution with k-states? All right, so what is the uninformative prior for, if I have a Dirichlet distribution with k-states? All right, so you have a coin that has k sides. What is the most uninformative prior, you think? You remember, based on what I said some time ago, maybe you assign probability to each side of the coin 1 over k, right? But guess what, if we do this calculation, and we do this calculation using the Fisher information, the uninformed prior comes to be 1/2, 1/2, 1/2, not 1k. So not only it's not 1k, 1k, and it's not even the Dirichlet distribution with parameters 1, 1, 1. That is not a well-known fact, but it's actually extremely important. So in lots of books, they will be using this, thinking it's uninformed, or using that. The correct uninformed Dirichlet prior using Fisher information is the one with parameters 1/2, 1/2, 1/2. Okay. Now, nothing is rosy with any theory, right? So there are pathologies. There are some serious issues that come with the Fisher prior. And let me just tell you one that maybe it's, if you think deeply, what's a prior? A prior is a distribution about your parameters before you see any data, right? But according to the Fisher information theory, how do we compute the prior? We use the likelihood, which means we use the data. So, this is, it's against anything based on the Bayesian formulas, okay? As a matter of fact, you can show that this Fisher prior does not satisfy what's called the likelihood principle, all right? Which goes beyond what I said. And what is the likelihood principle, right? So you can actually have two different formulations with likelihoods that they're proportional to each other, but the Fisher information will actually give you a different prior. So the Fisher information will be different, even though the likelihoods are proportional to each other. And there is a very nice example if you read this wonderful book on Bayesian statistics. You can see if you use a likelihood, it's a binomial, a negative binomial, both have the same likelihood, but actually the Fisher information is different. So that's another problem with the Fisher information. And there is a third problem, there may be more, all right? And I'm highlighting with an example using a Gaussian prior. I'm going to mention this with words only. There is a third problem. So let's say that your parameters are both the mean and the variance, or in this case, the mean and the standard deviation, okay? So if you compute the Fisher information, so since you have two parameters, the Fisher information is going to be a matrix 2 by 2, right? You're going to have to take derivatives with respect to mu and sigma, second derivatives, but also the mixed derivatives. So when you compute this matrix and you take the determinant and you take the expectation, it comes out that the prior for mu and sigma is 1 over sigma squared. Okay? So I repeat, the prior for the joint for theta, mu, and sigma is 1 over sigma squared. But actually, if you assume independence between mu and sigma, and you compute the prior of mu and prior of sigma using information, Fisher information separately, the prior of mu is uniform, and the prior of sigma is 1 over sigma. So if you use them together, you get the prior 1 over sigma squared. If you assume they're independent, you get 1 over sigma. All right? So that can be troubling if you think about it. Let me just bypass this. and I'm going to bypass that. The only thing I'm going to say, actually, before bypassing, whatever prior you use, right, you need to be sure that this prior introduces some robustness in your problem. And robustness means it does not pull your estimates towards the prior mean. All right? So if you see a formulation where you use a likelihood, you multiply by the prior, you do some estimation of the parameters, or you compute the posterior, and the whole posterior has shifted towards the prior mean, that's not good news. And the only priors that actually are robust, so they don't pull you too much from your likelihood, are distributions that have heavy tails. And it may sound as sort of an irrelevant little parenthesis topic, but it's a huge research area. And later on, actually, I'm going to show you, and maybe we will do a homework problem to see the robustness of distributions with heavy tails. And so if you work with the Gaussian, and the example I had on the previous slide, without going through details, the Gaussian does not have robustness as a prior. So do you know any distribution with heavy tails? You know what heavy tails means, right? It goes to 0 as you go to infinity and plus minus infinity slowly, and the tails are heavier than those in the Gaussian. So any distribution that does that? So the student t distribution, the Cauchy distribution, the Laplace distribution, et cetera, et cetera. So we will see that all of these distributions are going to come up later on in our lectures. All right. You know what? I may have time to actually do directly one example on the hierarchical Bayes, okay? And so you remember the idea of the hierarchical Bayes that, the empirical Bayes formulation that we discussed on the previous lecture was if we have some parameters theta and we put a prior on theta, right? We want to be sure the effect of that prior is not very significant. So if that prior has parameters, we put another prior on those hyperparameters. All right? So basically, we can call those parameters theta. So the parameter theta define theta, and then the likelihood is going to be defined by using theta that depends on eta. And I mentioned that what was the idea of the empirical Bayes formulation, which is huge? So how do we treat this hierarchy from eta to theta? So what is the empirical Bayes? So we're going to use a point estimate for eta, all right? And that point estimate on eta is going to be computed by maximizing the marginal likelihood, treated as a function of eta, where the parameters theta have been integrated out, okay? And now, again, someone will say, wait a second, I'm troubled now with this, because I know your head is spinning on a Friday, right? You are generating lots of ideas, and you say, but shouldn't the prior be independent of the data? And you are telling us you're going to fix it to some point estimate that somehow maximizes a marginal likelihood. That means it depends on data. That's against everything I learned in my previous class. And I tell you, yeah, I know, you learn things and then you forget them, all right? Because things are evolving, okay? So even though it doesn't sound that it follows the Bayesian paradigm, it works, all right? And I wanted to give you a wonderful example, actually, on how this hierarchical Bayesian thing comes to why do we need it, okay? So let me describe it in the 5 minutes we have, okay? So let's say that we have a number of cities. Each city has a population Ni, okay? And we measure the number of people in every city that has the coronavirus, all right? They're basically sick. So xi are the number of people that have that disease, okay? And that infection, and we're gonna take xi to be coming from a binomial distribution with some parameters theta. Now, if you go to certain places in China, all right, the population is big, and you have lots of people who have the disease, but if you go, let's say, to Singapore, maybe 3 people have the disease as of this morning, or 5, right? So the question is, how can you estimate the parameters theta for every city if in some cities you have lots of data, both you know the population, you know how many people are sick, but in other cases you know nothing. For example, will you say that this, so theta is the probability, right, of having the virus. So if, let's say, in a particular city x is equal to 0, does it mean that theta is 0? Right? The fact that you haven't had anybody identified having the virus, does this mean that the mean is there 0? The answer is no. So what is the whole idea of this hierarchical Bayes formulation is to actually link data across the cities to compute the probabilities theta I for each city. So use basically cities that have a big strength because they're big population with lots of people who have the disease, and try to use that strength to compute theta I for cities that either have very small population or their x's are very small. So how do you do that? You're doing this, but by actually linking all the theta parameters to be coming from another prior, right? So remember, theta, it's a parameter there. So I'm going to link those to be coming from a prior that has hyperparameters A and B. So rather than saying the thetas are independent, no, they're basically samples from a beta distribution with parameters A and B. And because these A and B are fixed for all the cities, right, it's the same beta distribution, effectively my calculation of theta will have to be done for all the cities together. So how do we actually do this? If you take, this is the normalized posterior, involves both the likelihood and the priors of theta and eta. So you're going to have, this is the product over all the cities of the likelihood times the prior of theta, all right, which is a beta distribution with respect to the hyperparameter theta. And then you have a prior on eta. And what is eta? Here is alpha and beta. Okay? So can you tell me actually how the empirical Bayes formulation will work on this problem? How we're going to link all the cities together to actually allow to address this sparse data problem? What parameters are we going to compute by maximizing some marginal likelihood? We're going to use the parameters A and B, right? So we're going to use a point estimate for those, and this point estimate will be computed by maximizing a marginal likelihood. So let me, before I do any of the algebra, okay, so let me give you some of the results, and I know the light is going to go off. So this is my 20 cities. You notice in some cities, like city 20, nobody has the virus. All right, some cities have huge populations, and some have smaller populations. So this, what you see in the third plot, is the MLE estimate. And the MLE estimate for each city is how many people have the disease divided by what's the population. All right? Notice some cities have 0 MLE because there was nobody with a virus. All right? Like city 20 has 0 MLE from what I can see, okay? And what is this red line here? This is the pooled MLE. So if you take all the cities with all their people with the virus, divide by the total population of all the cities, this is the pooled MLE, okay? So obviously, you can see the MLE estimate is very bad, right? It predicts zeros in some places, some huge estimates for some cities where you had a lot of sick people, but it doesn't look appealing. And now on the bottom, what you see is you actually see the posterior mean. And notice, cities that had 0 sick people, all right, now have something, all right? The posterior mean is not 0. You can see city 1, the posterior mean is not 0. And how do you calculate the posterior mean in the parameters theta? Basically, it comes out that the posterior mean is an average of the MLE, all right, and the pooled mean and the prior mean, if I can say. The prior mean, you remember the parameters theta follow a beta distribution with parameters A and B, so that prior is A divided by A plus B, but the question is, how do you compute A and B? And the answer is you compute it by maximizing what? I can go very fast. The time has gone by basically maximizing the marginal likelihood as we have done before. So you can actually compute this. You can maximize it and compute the parameters A and B. You can do this calculation, by the way, analytically. You should click the computer program, and you can get these wonderful results that I'm going to give it to you as a homework, so you can actually even produce the confidence intervals and explain to me why, for example, city 10 has such a huge posterior uncertainty. And if you look at actually city 10, all right, the Melie estimate of city 10 is huge. All right, so it's like because the population is big, the sick people is big, MLE estimate for city 10 is big, but you know what? When you share information between all the cities, the posterior estimates shrink. You can find some mistakes and come and tell me that as well.
So, as we know, I know that I've said to this class before, in the Bayesian paradigm, excuse me, model parameters are basically treated as random variables, and they're treated as uncertain, and we model those parameters by means of a prior. The idea here is that in some cases, it's even more beneficial to basically take that one step forward, further and basically decompose your prior knowledge into essentially multiple levels. This is particularly when the data here is hierarchical. So in many merits, think about, so if you have a prior, so what we're going to do is we're just going to put a prior on that prior. And then that will be basically our then Bayesian kind of formulation. So particularly this is referred to as hierarchical Bayes methods, and they're a powerful tool that for expressing a rich statistical model. So obviously a lot of models can fall underneath this category. So down here, kind of looking at these equations. So again, in our usual Bayesian fashion, what we do is that we have a likelihood term. We have some, so this is like some data or some our actual features. And we have some parameters that our likelihood is basically dependent on. And then in our Bayesian way is that we introduce a prior onto these parameters. So in this case, let's say we have 2, it may be beneficial to instead of having a joint here for both of these parameters, is to rather decompose it into essentially a set of priors. So here is instead of having a joint prior, is that we have a prior on theta given phi, and then basically a separate prior on phi. So essentially we now have two priors here. And basically this is the simplest example of a hierarchical Bayes model. And basically the philosophy here is that this concept can basically be essentially recursively repeated down deeper and deeper. And the motivation of this is that the deeper we go by stacking priors, the less influence those priors will have, and the less of a concern of the actual form of these priors actually play in our final predictive distribution. So clearly this prior down here on phi is going to matter, the form of it is going to matter a lot less than perhaps the prior on theta, because the theta prior has a lot more influence with the likelihood. So yeah, so that's kind of like the general philosophy. And as I said, essentially, eventually though the process must terminate. Like it doesn't make sense to go further. Yeah. So here, we just consider consider like an n-level hierarchical Bayesian model. So you can see here, essentially, this is again kind of like that, that recursive type formulation. Basically, you have a whole hierarchy of basically priors that go all the way down to theta m here. And of course, this seems fine and dandy until you want to compute things such as like the marginal. So now instead of just marginalizing over one parameter, what you now is that you now have a marginal over a full set of parameters. So that's kind of like that's the trade-off that you're taking, is that although you're introducing maybe some more descriptiveness and your model can be more flexible, basically that comes at the cost of potentially conducting actual inference may be a lot more difficult. So in this case, let's just for just kind of demonstration purposes, we just consider a two-level hierarchical model. So in this case, again, we have our likelihood of our data, so it's x. We have some parameters theta, and then conditioned on theta 1. So basically, these are the hyperparameters of the prior, and then we're modeling the hyperparameters of the prior with the prior. So it's like prior with prior. So yeah, so just some terminology. The full posterior here, right? So the posterior says what is the probability of our actual model parameters given our data. Our data is x here. So the full posterior is basically like the joint. So in this case, we have theta and we also have theta 1. Similarly, we can also define variations of this posterior. So we can have a conditional formulation of it, of essentially what we're doing is that we have a posterior of just theta. Instead, what we're doing is we're conditioning it on theta 1. So this is the hyperparameter of the prior, and then also our data. And then finally, we can also have a marginal. So in this case, we're marginaling out theta 1. So this is like the joint. This is the joint posterior here. So this is the combination of all three. And then marginalizing out theta 1. So basically, the result is that all we have left is the original actual posterior of our usual Bayesian framework. So a key requirement for computing the posterior is basically the specification of the prior. So this was in the previous slide. This was theta 1. So yeah, so basically we have some hyperparameters, and the merit here is that what if we don't really know how to deal with these hyperparameters? In many cases, we can just use uninformative priors. So basically, these are just uniform priors. And this is again the spirit of hierarchical Bayesian method, is that rather the true Bayesian way is to put a prior on your prior, which then goes on your likelihood. So yeah, so in terms of like a graphical model approach, you see that the dependence of our data is directly dependent on theta, but theta is then directly dependent on type of parameters. So yeah, so this is a multi-level model. So you can see that each one of these can represent multiple levels, with the hyperparameters being more global and going all the way up to our actual data. Yeah. Okay. So this was, I believe, the example that he. Professor Zavaris went through pretty quickly, but so we're going to go through it again. So to kind of demonstrate this, the idea of hierarchical Bayes, we're going to consider modeling cancer rates in cities. So just predicting if we have a certain amount of people in a certain city, how many people do we expect to actually have cancer? And this has obviously a pretty important applications. This could be instead, how many people in a certain city has a certain virus. So it's particularly prevalent to the time it's being reported. Yeah, so we have various cities where NI is the number of population, and we have people who died of cancer is basically XI. So we would basically model this through like a binomial distribution. So this is like your standard, I have N, choose K. Yeah, so then basically this has a hyperparameter theta. So theta is like the probability of essentially the cancer rate. And we can either estimate them all separately. So the idea here is that we could, let's say if we have this model for, the number of cities, if we model this separately, we just did kind of like an MLE, basically this would really suffer from the sparse data problem. And if you remember, at least I talked about it a week ago, I believe, is when I was in here last. This is similar to that idea of what was referred to as the black swan paradox. Basically, a lot of the times in the case of sparse data, we don't have all the possible observations. So, and to be truly rigorous, we need to really account for data that we don't have. So in this case, so basically underestimation of the rate of cancer due to a small population. So basically, if we compare, two towns or cities, so we compare like New York versus South Bend, right? Obviously, the New York, just due to its size and population, is going to be a lot more influential if we just did like an MLE estimate here rather than South Bend, which maybe we have very few samples of people dying of cancer in South Bend because we have, such small number of people. So, so in reality, that's a problem that we need to figure out how to deal with. So we can assume that theta I is the same, or are basically all the same. But basically, this assumption. So one way, the intuitive way would be, okay, each city has their own cancer rate, right? So maybe one city has more air pollution than the other, or maybe they're, closer to some output from some factory, so maybe they're higher. The other assumption would be, okay, maybe all the cities, maybe it's just like a national percentage, right? Everyone has equal probability of getting cancer. But, that's a rather strong assumption, and I don't think a very good one. So the idea is that as a compromise, we're going to say that the probability is basically very similar between cities. Now, they can be different, but, at the end of the day, humans are humans, so we shouldn't expect it to vary a whole lot. So what we're going to do is that we're going to revisit a hierarchical version. So basically this right here, this component right here is our old friend, our binomial beta model. So if you remember from, I guess for you guys it's now been 5 lectures ago, this was originally introduced in the discrete generative model lecture with modeling coin flips. So basically here now what we're doing is we're using the same model, but now we're modeling basically cancer rates. And basically, so we have our binomial likelihood here, and then we have a prior on the theta parameter, represented by the beta distribution with a hyperparameter, which then has its own prior. So particularly with these two, right? So the beta is a conjugate prior to the binomial, so that means that the posterior will also be a beta distribution, right? That's why we use it, and that's why we use conjugate priors. Yes. So in this case, what we're doing is that we're treating the hyperparameters of our prior as basically unknown. So this allow for the poor data in cities that basically, so this allows for cities like maybe South Bend, to borrow statistical information from data-rich ones like New York. So the idea is that we can pull global information and help influence our local information where maybe data isn't so rich. So this is kind of an example of an example output. So this is, again, we're kind of going, we're going kind of 2 steps forward, and we'll kind of reverse a little bit, talk about how we got here. So we can see that up top in this graphical, these graphs, basically this is our sample of the number of people that essentially with cancer. And so x-axis is essentially the index of the particular city. And then y is the population. And we can see here that this is the population of the actual city. So we've kind of truncated it at 2,000. And kind of the key here with our data is, is referring to kind of the black swan paradox in our sparse data problem, is that you can see that actually for many cities that have, a pretty moderate population, we just don't have any data. So what happens in the context of MLE, so this is without any sort of priors, any sort of Bayesian approach, what happens is that you just say, okay, your model, it just sees that, okay, I have no measurements of people having cancer from the city, so this city's cancer free. And obviously that's not a good thing. That's not what we want. We know for a fact that that's not true. So now what we do instead is that now we take our hierarchical Bayesian model. You can see that actually essentially what's happened is that we basically induced some probability. So we borrowed some statistical knowledge from these larger cities with more observations. And you can now see that even though some of the cities, they don't have any observations, they have a non-zero probability of actually having, a certain amount of people having cancer. So regarding, if you remember, previous lectures, we kind of talked about this with the beta binomial model, of the benefit of even just having this. Essentially, even if you take this beta distribution as a uniform, right, what you get is that you get a +1 smoothing effect. Do you remember that? So the idea with the example that we talked about was if I flip a coin, and I maybe have 3 observations and they're all heads, right, and I'm trying to figure out theta in the coin example is what's the probability of heads and tails. Basically, having the beta prior adds on prior probability, that the fact that we could observe tails in the future. While an MLE estimate would basically just remove chances of a tails, because we've seen all heads. We've seen 3 heads, so we just say the coin is 100%, heads, and we will never see tails. Which we know for a fact that's not good. So the same idea is basically being applied here. So this is kind of showing the credible intervals. So this is kind of like the standard deviations here. So some cities of interest here are basically denoted. So city 19, 15, and then 10. So in this case, the y-axis is our index, and then our x-axis is basically a probability of cancer, and then basically we have this little star is our mean. And then these bars are basically our 95% confidence interval. So particularly we can see that with city 15. So city 15 had a very large population. So what this means is that, for this particular city, we have a lot of data coming from it, right? So it makes sense that actually the uncertainty on the parameter theta, that we can be pretty confident of it, right? And we talked about this before, is that, as we increase samples from particular area, our uncertainty should decrease, because eventually the posterior, given infinite data, should converge to the MLE. So that's kind of what this is showing here. In other cities, so in the case of 10 and 19, which basically they have maybe the highest MLE, but basically here, they have a very large posterior. So essentially, this is showing that although these cities, in an MLE case, we may be very confident in them, but what they're doing is they're conflicting with our posterior. So if I remember correctly, it's like, let's see here, 10, 19. Yeah, so in particular with these is that they're there's some outliers. So 10 and 19, they have a lot of people that have cancer, but their population isn't super large. So relatively speaking, compared to some of these larger cities. So what that's doing is that's conflicting with our prior knowledge of, remember our prior with the beta distributions, basically we're saying that, hey, odds are the cancer rate should be relatively the same. So what happens is that when we get an outlier, or we get some data that really doesn't agree with that, our posterior basically adjusts for that by introducing higher variance, which just lets us, this kind of gives us some red flags. Practically speaking, this gives us some red flags to say, hey, maybe if you're actually conducting these studies, maybe these cities, maybe we need to go resample, maybe we need to check them out, or maybe they are real, but maybe this data is fully correct. Which if you want to decrease the uncertainty, you just go and you get more data, just like city 15. Okay. So in the case of the hierarchical Bayesian model, we have the joint posterior now, right? So we have the actual, so we have the likelihood with the likelihood type of parameters, and we also have the prior type of parameters. So we have this joint. So basically, again, the trouble is that when actually finding the posterior over the theta, so basically to estimate the hyperparameters on the prior, right, we would have to marginalize out theta. So that's kind of posed down here, right? So let's say we want to compute this this distribution here. We would essentially have to marginalize out theta from the actual joint posterior, and in many cases, yes, we can analyze. So we would have to marginalize this out. In many cases, this is possible because of the way we define these, we can use like a conjugate prior, so we can actually do that. So to approximate our actual hyperparameters of our prior, what we do is that we can actually take just a point estimate. So this is basically kind of like a map estimate of what we're doing. So in this case, this distribution, we just approximate it as the posterior of our hyperparameters of the prior, and this is equal to basically the maximum of the marginal. And this is basically possible because our hyperparameters of our prior are essentially, they're typically much smaller in dimensionality. And this is talking about, kind of this hierarchy or this multi-level type system of basically, maybe you have higher dimensions here and you have lower dimensions here. So again, these maybe have some more global meanings, or these have some more specific feature meanings. So basically by taking a point estimate of, parameters that are deeper into our hierarchy, we're much less prone to actually overfitting them. And the quantity inside the brackets is the marginal likelihood, which is also referred to as the evidence. So in general, this approach, by taking a map estimate of our hyperparameters of the prior, this is referred to as the empirical Bayes method. So this is an approximation, but usually this approximation, again, is pretty good. Similar to kind of like the naive Bayes classifier. Sometimes you just make an approximation because it works well in practice, and it makes inference actually a whole lot easier. So actually, I like this table a lot because this kind of illustrates different levels of basically kind of Bayesian formulations here. So you can see that, the most basic would be the maximum likelihood estimate, where we just kind of have we just do MLE. We have the map estimate, so this is like our standard approach. Basically, we just have, we have our prior on theta, we set some hyperparameters, and then we just find the map. We have, so kind of one step further, more descriptive, would be the empirical Bayes method, where basically now we have a map estimate, rather than a map estimate on the prior, we have a map estimate on the prior's hyperparameters here. And then we also have a map 2, and then we have the full Bayesian, which is basically you essentially account for everything. You don't take any point estimates, you're doing everything, you're doing all the marginalization, everything. So an interesting note here is that empirical Bayes violates the principle that the prior should be chosen independently of data. So originally, when doing Bayesian, our prior, we don't want really let our data influence our prior selection too much. We want our prior to basically encode some prior information that maybe we have about it, but we want the data to really be in the likelihood. And then the problem with empirical Bayes is that actually what you're doing is that you're selecting the hyperparameters based on this distribution here, which is actually, this is essentially this is the marginalized likelihood, right? So it's not the probability of the hyperparameters, it's the probability of the data. So in some sense, you're kind of doing almost MLE on the prior's hyperparameters. So this isn't actually like a posterior here, right? This is the posterior down here. So this is kind of reverse of what we used to think about, what we try to avoid with Bayesian. But basically, this is, as we say here, this is kind of a cheap approximation that we made, which can work pretty well. So it's just kind of like an interesting side note of how this kind of conflicts with the Bayesian philosophy. Okay, so returning to our example here. Basically, again, so modeling cancer rates in cities. So we have this binomial likelihood, and we have our beta prior. And then essentially what we've done is that we've marginalized out, this is the marginal likelihood. So we've integrated theta out. That results in the following here, where b is basically the beta function. Now there's multiple ways to actually maximizing or figuring out what A and B should be. Tom Minka, when you search for a lot of this, whether it be, for example, if you have like a student t distribution, or in this case the beta binomial model, or if you have some combination of distributions and stuff, and you're trying to find some priors, you search for it, odds are you'll find some little 5-page PDF by Tom Minka, written back in kind of the early 2000s, and discussing of essentially the approach for it. Yeah, so really kind of a big legend in the Bayesian community. So assuming that we have maximized it, skipping how we're going to do it. So essentially assuming that we have it estimated, we have some point estimate of A and B, we can then plug in these hyperparameters to compute our actual posterior. So what we do is that through some method, we maximize this. So it's like an MLE estimate, right? So we're maximizing the probability of our data given A and B. We maximize it, and then we take these point estimates and we plug them in, and then we can then compute basically a posterior here. So then we can continue and do our usual Bayesian tasks that we've discussed prior. We can then go and compute a predictive. If you just want to map, you can then just compute the map of data. But the idea is that by taking a point estimate of A and B, it's a lot better than just taking a point estimate of theta. And then so here, kind of again the merit, a key point is essentially because in this case, right, so A and B is shared among all of our cities. So you can see A and B don't have an index I. So these are global parameters, and when you compute them, they are computed based on the global data. So you can think that these parameters, these are the ones that are grabbing statistical information from our other cities and pulling them into the ones that maybe we don't have any observations. That's where this information is basically being transferred through. This is like these A and Bs are basically kind of like the proxy for that, which is what is being said here. All right, so another numerical example. So consider basically a real value problem. So no more discrete data. So a real value model. So we're going to talk about a Gaussian model. So in this case, the Gaussian, so here we're just trying to estimate some scores on basically a test. And we have different schools. That's kind of like the background to our little toy problem here. So the sample, the key here is that, for some schools, maybe like, for example, this could also be like Notre Dame. Maybe we have a lot less students than maybe some larger college, like University of Maryland or, some of the larger universities. So that means that we have, in terms of our statistical influence, maybe it's hard to get really good inference here, because if we don't have really good samples from our relatively smaller college, that could pose a problem with trying to do inference. So again, what we're going to do is we're kind of take a hierarchical Bayesian approach, empirical Bayes, So what we have is that we have a likelihood. We have two parameters. This is a Gaussian. What we're going to do is we're going to assume that the variance or the standard deviation is basically known. So what's really unknown is the mean. So theta. Theta is the mean of the actual Gaussian. And basically what we're going to do is we're going to assign a prior on this mean as a Gaussian. So in the case of the mean, so the conjugate prior of the mean for a Gaussian likelihood is also a Gaussian. So this combined with this will make a Gaussian also. This is not true for the variance. In fact, this won't work for the variance, right? So ideally for the variance, we don't want to assign a Gaussian prior because, well, in the case of, it can't be negative. So we want to choose a distribution where we don't have negative numbers. So that'd be like a gamma distribution, or in the case of an inverse gamma distribution, if we had that, that would result in a student T posterior. Or with the heavier tails, which I believe you guys discussed in the slides before this. And then so our prior here then has mu and also tau. So these are, in this case, these are our hyperparameters, which we will want to basically find a estimate for through the empirical Bayes method. So if we work out all the details, so kind of skipping over all the math associated with it, basically what we end up with, so we compute like the evidence and we compute the marginal. What we end up is at our actual priors, so down here in the blue. So down here in the blue is basically the result. So this is the probability of our data given our actual hyperparameters. Hyperparameters here, and also we know the variance, right? So in this case, to actually compute this, we would have to marginalize out theta and basically compute this through, it's just like kind of like an MLE estimate. And so we end up with the following. And we can kind of see here is that these are basically global estimates. Again, these don't have J indexes, so they're being influenced from every single school. And you can see that essentially what's happening is that our mean of our prior is essentially, it's the mean of basically kind of like the empirical means, right? So we're taking mean of the mean is then the mean of this, which fundamentally that makes sense, right? And then similar for the actual, the variance here, follows in a similar fashion of basically, well in this case we have the addition here. So the actual empirical variance subtracted by the known variance here would then be a tau. So it follows from this that the posteriors are as follows. So what we do is that we have these global estimates. So this is computed with the evidence approximation. So we compute these from all our data. We have them. We take a point estimate because we're doing empirical Bayes. So that allows us to basically plug them in, and then we just have a posterior, which is in the following form here. So you can see kind of the influence of our priors coming in here, and B here contains tau. So that's where tau is. So so normally the way that you would do this, right, is that you would have the two Gaussians, you combine them together, complete the square, and you result in your posterior. So it's kind of saying here, this is some of the same things I just said. So basically, it's similar, just talking about the obtaining the actual priors. This right here, this is showing the actual marginal. So I mentioned on the previous slide is that actually what we want to do is that we want to compute the marginal likelihood, right? So we want to marginalize out theta. So basically we can get the distribution of our data given our hyperparameters, right? So this is empirical Bayes, and what we do is we find the maximum of this to get a point estimate. So it's like computing MLE for this particular likelihood, but we're replacing theta with our hyperparameters. And if you work out all the math, it's this, which was on the previous slide. And then basically, in general, we use this term right here. This is just to make sure that this term doesn't go negative. That's all what this is. And as another note here, for a non-constant, so in the case that the original variance in the likelihood is not constant, we would use expectation maximization to actually derive the empirical Bayes estimate. So basically, we would have to require some more involved inference methods to get some actual, to compute these point estimates. Yeah. So it mentions also here full Bayesian inference is also possible, but I would assume if you're going to be using expectation maximization, it's probably not the easiest thing in the whole world to do. Yeah. So the key insight in empirical Bayes is that the use of priors. So use priors to keep your estimates under control and obtain priors empirically from the data itself. So we'll obtain the priors, but basically obtain the hyperparameters of the priors. Yeah. And yeah, this is just some additional terminology. So this James Stein estimator is one particular form of this hierarchical Bayesian approach, where basically, essentially, if a particular form, the variance over this particular form is basically constant between all. Just kind of looking though, so looking at this formulation here, just kind of looking at like what exactly is this doing, what exactly is the prior and like this hierarchical approach, what is it actually doing for us in terms of the actual posterior. So you can see that actually what we have is that we have kind of like almost like a mixing parameter here through B. So as mentioned here is that basically the quantity B hat basically controls the degree of shrinkage towards the overall mean mu. So this kind of interesting insight is that, so if B, in particular B, if it's close to 1, we can see that basically this term, so this is the mean for this particular school, right, because we're doing test scores. This goes to 0. And what we do is that we tend towards the global, the overall mean, which again, this is mu hat. So this was estimated, this is our point estimate from our hierarchical approach. So this is estimated from our global data. So this is all the schools. As opposed, if B is really small, what we do is that we tend towards the individual school's estimate. So basically, if the data is reliable for a given group or a given school, J, then basically what happens is that the sigma for that school, it will be small compared to the global variance, tau. So basically, that means that B in general will be also relatively small. So in this case, if we have a lot of data, right, maybe that data is all very consistent. So for this particular school, the variance for that particular school isn't super large. What that does is that makes B very small. So that basically lends weight to that actually school's mean. So that says, hey, we have a lot of data. We should be really confident in it. So let's just use our computed mean from just this particular school, more so than the global. On the flip side, if we have a lot of variance in the sample, so maybe we have 3 samples and they vary greatly, we have a lot of different test scores, right? Basically, the result is that this B becomes relatively large. And then what that says is that, maybe we shouldn't be so confident in these samples. We don't have a lot of information about the school, so let's rotate more and let's use the global estimate more so. So that's kind of like the more kind of intuitive regularization interpretation of using a hierarchical Bayesian framework. All right.